Thank you very much. Thank you, everybody, and good evening. Good evening. Thank you very much, and I look forward to the next hour or so, just under hour, to talk a little bit about the work that we've been doing at the university, particularly around the invisible evidence and the role that chemistry plays in solving crimes. And as Chris mentioned, there is a nice beach ball behind here. All will be revealed in a minute of what that's going to be used for. So just a little bit about myself first. So who am I? I am first generation into university, so I'm the very first one within my family to have entered into university. My parents are extremely proud of me, as are my extended family, my husband, and so forth as well. And I'm also the head of department at Kingston University, and I lead the department for the chemical and pharmaceutical sciences. My PhD was mostly focusing on analytical techniques that are used in materials analysis and medical materials. So my PhD was mostly focusing on intraocular implants that are inserted into the eye, and some of the techniques that can be used to actually analyze some of the excipients and the things that come out of those materials and whether they're good or bad for us. But you're not here to listen to that today. You're here to talk about forensic science or learn more about forensic science and the role that chemistry plays in that. So some of those techniques that I was utilizing throughout my PhD, they overlap with the area of forensic chemistry, and particularly they overlap in relation to some of the techniques that I will be exploring today. So on this time that we have with us together today, I will be going through some of the details in forensic science. So some of the information around what we see in forensics and the TV, the media, but the reality of actually what happens when you explore forensics in the greater context of chemistry. I'm also going to explore what's known as Locard's exchange principle, which is the basic fundamentals of which forensic science is built upon. It's the way in which we engage individuals to understand how can transfer take place from a crime scene to a suspect to a victim and so forth. We will then start exploring a little bit deeper into the chemistry aspects to do with spectroscopy. It's a particular technique that's used in evidence examination, as well as chromatography, which I will demo to you on how it actually is utilized in a forensic setting. I will then move on to talking a little bit about some of the forensic research that's taking place within the area that I work within in the university, and then I will move on to what the future might hold for forensic science, and how can we embed more of chemistry within it to uncover some of those things that still we don't know about. Just a bit of a pre-warning, we will be discussing some real cases as well, so wanted to warn you that they'll be peppered throughout the case as well. There won't be any graphic images, but I will be talking a little bit about some of the cases that are presented and you may have heard of in the media before. So let's get stuck in. I've got a very short video to play that I wanted you just to reflect on, looking at this particular video. Is there anything you notice whilst you're watching it? And all be explained in a second.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you?
Action.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
So, that was just a quick video just to demonstrate to you that actually when it comes to observation, what you see necessarily doesn't mean it's going to be what's presented in terms of evidence, what might be underlying it, so the uncovered evidence. So this is where chemistry is applied. So the principle that I wanted to present to you was Locard's exchange principle. Locard's exchange principle is based upon the concept that every contact will always leave a trace. And this was from Dr. Edmond Locard, a very famous French scientist who discovered that there will be an element of contact and trace evidence left behind when contact is made. Cue the beach ball. So let me go and grab the beach ball very quickly. So at this point, just to warn you, I'm going to pass this around. So just be careful of not knocking anybody out in the process, and the cameras as well, please. So I'll pass it over, so feel free to pass it round. And that was such a bad shot. We'll get there in the end. Let's pass it this side. So you can see several individuals are actually involved in touching this particular ball or beach ball. I'll just pass it around here so you don't feel left out. So at every opportunity that somebody has touched this beach ball, there has been some element of contact taking place. And when we're referring to that contact, there will be some sort of physical contact that you have, which is fingerprints. But not only fingerprints, there is likely that if you're anything like me that sheds a lot of hair, you probably have left traces of hair behind, even in that very small amount of contact that you have made. So bear in mind and keep this concept throughout this whole talk, because that's something that's really important as the basis of how forensic science operates. The other thing I wanted to introduce you to was this contact of trace leaving an aspect of trace components when we are looking at almost this golden triangle. So I'm just going to show on here. So when you're looking at this golden triangle, which was the concept that was introduced by Dr. Edmond Locard, he indicated that if there is a victim and there is a crime scene and there is a suspect, there will be elements of contact that have been made at some point. So if the victim has been in contact with a suspect, and that suspect has been in contact with the crime scene, there must be a way in which we can try to link all those two together, all those three together, to identify perhaps who was a suspect involved and who was a victim and how the contact took place. So that is the basic principle behind whole of forensics and the exchange of evidence that we see. So cue one of the evidence or one of the case studies that I'll just be very briefly going through. So this was a particular case to do with Emma Falls. It was a murder that took place quite a while back now, and it was to do with a body that was discovered in Galloway Forest Park. And this particular body, potentially, there was a suspect that they had, which was Ross Wilcox. And as you'll notice from this particular scene here, it was covered in a very large area. So the only way they're going to be able to identify who the suspect is, if they had a suspect in mind, they need to try to use that triangle concept to place the suspect at the crime scene and also in contact with the victim. So in this case, if you see the image there of the boots, it was the Timberland shoes, other brands are also available, but it was the Timberland shoes that were there that actually they found trace amounts of soil that were from the same origin as the soil from the actual crime scene itself. Alongside that, that wasn't enough. That was just able to identify the suspect had been at the crime scene. So now we have to think about how can you ensure that you can place that contact between the victim and the suspect. So they were able to analyse things such as the vehicle of this suspect, so Ross Wilcox, and they were able to identify DNA that was found in their particular vehicle that belonged to Emma Falls, as well as other items that were also belonging to the victim as well. So that golden triangle places those individuals in relation to the particular scene itself. So, as I demonstrated the concept of the beach ball, for those of you that are at home and are viewing this online, and for those of you that wish to do this at home, another way in which you can imagine that contract and trace element is if you're at home, if you were to take some pepper and you were to just simply place it onto a white surface, you then take your hand and place it onto that peppered surface, then attach it to another surface, you'll see there'll be elements of that pepper transferring over. And as they transfer over, you'll notice that that is what transfer is in terms of the transfer of evidence or the transfer of pepper. If somebody else was to then go along and touch that same surface where you transfer the pepper, there is a chance that they will also get some pepper on them as well. So therefore, you're having a contact trace effect, but not primary, secondary transfer now, which we'll go through in a little while as well. So forensic chemistry, and how exciting is it, and what is it? So forensic chemistry essentially is the way in which we apply chemical techniques to be able to examine evidence. And that evidence is sometimes unseen, and we're providing that voice to the evidence to make sure that actually we can see what it tells us about the circumstances of the case, but equally it's something that can be applied microscopic level or on a molecular level. So when we're looking at things that are very small, maybe we can't actually see them with the naked eye, so it enables us to be able to do that. However, one thing we must note is that normally this evidence is always mixed with what I'm going to term as noise. When we're referring to that noise, it basically means that whatever you're trying to identify in that evidence, in the case of the Emma Falls case, the soil's not going to be sitting there shouting out, oh, I contain potassium, I contain this, I contain that. So therefore, that extra noise that exists in that soil needs to be filtered out somehow so you can identify that it's the soil that comes from the same source as the one from the crime scene. So in this case, that external noise, if we try to imagine it a different concept, the one that I always like to try to explain it with is if we were to imagine making a cup of tea. Sorry for those coffee lovers, but I prefer tea. So if you're making a cup of tea, normally standard practice, you boil the kettle, you take a tea bag, you put some milk in it, you put some water into it. So when you're looking at all that external factors inside there, if I only wanted to measure the caffeine content inside the tea, everything else that you're seeing there, that would be considered as the noise, or the stuff that we're not interested in. So if we're not interested in that stuff, we only want to focus on the caffeine. So whatever technique we're using has to be sensitive enough to be able to identify the amount of caffeine that exists there. So one technique that we tend to use is something known as spectroscopy. Now, spectroscopy is a very powerful technique where it enables us to be able to use light, whether it's infrared light, near-infrared light, or any other type of light that we have, that we shine at a sample, and that sample will be a material of evidence of some sort, or it could be a solution, it could be a whole number of things. When we shine light onto that particular sample, what will happen is the molecules inside that sample will either absorb the light, they'll transmit it, or they'll completely bounce it off and reflect it. How it interacts with those things inside that solution is all dependent on what the solution or that sample is made up of. And then we will get a signal at the end that's transmitted. So that is the basic fundamentals of how spectroscopy essentially works, if we're trying to explain it in a very simple nutshell. So another example of a case, the David Watkins murder back in 1993. And this was a particular murder where there was David Watkins, who was shot dead in Pingewood, and there was a potential suspect again. Now, this potential suspect, Andrew Everson, they found 5 different populations of fibres that were discovered not only on the clothing of David Watkins, that weren't belonging to David Watkins himself, so the victim, but they also found in the seats of the suspect also fibres that belonged to the victim as well. In this case, what we were trying to work out, or what the forensic scientists were trying to work out, was trying to work out how could that contact have taken place. Was it direct contact? Was it indirect contact? So was it because the two knew each other, so therefore they were regularly visiting in the vehicle? And so when they're regularly visiting in the vehicle, you would expect to see those fibres there anyway. If it's direct contact, then we would find a certain amount. If it was indirect contact, again, a certain amount would be expected. And what you can see here, that's shown on the images over here, are some of the infrared spectra that were collected. So infrared light was shot at the fibres that were found, or put through the fibres, and then it produced this particular spectra that identified to us what particularly could be the dyes inside those fibres, what else existed in the fibres, so we can identify what it belongs to. So that was another example of a case where it was used. So I'm going to move on to some more stuff that's related to some of the work that I've been involved in, which is to do with cosmetics. You're probably thinking, cosmetics and fibres? How do they connect? Actually, they connect quite a lot, because when you look at fibres, they also contain trace components of certain constituents, whether they're dyes, additives, anything else. Remember the tea bags concept? They have a lot of other noise inside them, not just the dye. So in this case, some of those trace components are things that we were going to be analysing, but also they are complex compositions as well, and this is cosmetics in particular. So when we're looking at cosmetics, they'll be made up of, say, oils, waxes, preservatives, dyes, pigments, a whole range of things. And all those cosmetics will have a wide combination of different concentrations or different amounts of each one. So what we would be interested in knowing is if we had a trace, which is what trace analysis is, if we had a trace that was found at a crime scene, whether it was found on a victim, a suspect, a glass, an object, could we identify what the cosmetic is just from looking at it using some sort of techniques? So crime and cosmetics, how bizarre is it the two could actually be related? But technically, when you're looking at crimes against women, crimes against any sort of individual where there is a transfer of evidence taking place, whether it's through liquid, lipsticks, eyeliner, foundations, eyeshadows, one thing about them that they are easily transferable. So when you have these formulations or these powders, these liquids, however they may be, they can easily transfer from one surface to another. So the surface being where they're originally applied, and then directly onto, say, clothing when somebody's rubbed against them, or they can transfer onto objects in an environment and a room as well. So bearing in mind this concept, if we're focusing in on Edmund Locard's exchange principle, if we were to look for trace components of cosmetics, could we identify where they belong to? We think it's quite simple like that, but actually it never is that simple. Locard's exchange principle actually explored already cosmetics as forensics evidence back in 1912. The whole principle was based on the fact that there was a very famous strangulation and a potential suspect that was involved, and this potential suspect had their fingernail scrapings taken, and underneath those fingernail scrapings, they were able to identify cosmetic powder from the victim. So they had already explored using cosmetics in forensic settings or forensic examples back in 1912. So it's nothing of a new sort of concept that we're thinking, wow, this is amazing, groundbreaking, but actually they could identify that there potentially was some sort of powder and it matched that same powder. There are further complications because obviously when you consider things such as cosmetic brands, with cosmetics you will have a brand. Let's just say Chanel. There are various other varieties also available. So if you have Chanel, Chanel will have a specific red color. But not only will they have that red, they'll have variations of that red. So how can you distinguish one red from the other? You can't see it just with the human eye, so you would need to use some sort of chemical testing. So a good example that I will always refer to is the dress example back in 2015. There was a huge craze all over the internet. Everyone was arguing over whether it was it seen to be a gold and black dress or was it a blue dress? So what I consider as being a red Chanel number so-and-so, somebody else may think, well, actually, that's a bourgeois so-and-so, or it's a YSL so-and-so color. So therefore, by the naked eye, you can't actually tell what it actually specifically is to that minute detail. So therefore, when you're looking at these particular brands, they will have their own versions of red within them, but also across different brands, they will have their own formulated and patented versions of what their red is. So if you had a Ferrari red from one particular brand, their Ferrari red version could not be the same as that particular brand because they're patented. So therefore, there will be different brands as well that have different types of red. What type of clothing could it be transferred to? So very easily, if you were to take some lipstick and you're putting on some lipstick, you could quite easily just transfer it straight onto your clothing. But what type of clothing an individual is wearing is going to be that noise as well. So now we've got several layers of noise. Not only do we have the noise that exists in the lipstick itself with all the other stuff in there, but we also have that noise from the fabric that the individual is wearing. So the technique, whatever we use, needs to be sensitive enough to be able to identify that this is a particular type of red belonging to this brand. So what we did is we used near-infrared spectroscopy, and it's a non-destructive technique. Non-destructive meaning that we were able to take a fabric which had a smear of lipstick on it, and we're able to directly analyze it using the instrument. And nowadays, technology is getting much more advanced. You actually can have handheld near-infrared instruments. So you can have a handheld device that will enable you to be able to test things straight away, and it's quite portable, rather than taking it to a laboratory, which could be quite useful for doing stuff at the crime scene. There is little or no sample prep needed, purely because it means you don't have to do anything to treat the sample beforehand. You can just run it as it is without it having to undergo any chemical processes. If you were to do any chemical processes, you could potentially damage what you have there. So the sample is focused on with near-infrared light. The molecules will absorb some of that light at specific wavelengths. And when we say wavelengths, it basically means how the molecules will interact with the light, how they get excited, not excited, and they will be collected on a spectra. And that spectra will then hold very useful information for us that we can then use to identify what an unknown might be. So we started off this process by building a database with known samples. So the PhD student I had working on this very excitedly went off and purchased loads of different versions of red, different versions of pink, different versions of all the different types of lipstick you can get. And they started building a database with these known samples. And now these known samples, when they produce them, you can see, just from looking at the image here, those red lipsticks, again, there's several different varieties there. Those red lipsticks, if you look at them on the near infrared, they look very similar. There doesn't look like there's much difference between them when you're looking at the spectra that you see here, or the picture that depicts whatever came out the instrument. So you're probably sitting there thinking, okay, so what's the point of doing this then? Because it just looks like you plug it into the instrument, and it's going to give you something that just shows that they're all red. How do I know what type of red it is? We also tried the same with foundations as well. So we took away some foundations and we decided, okay, let's have a look to see if the foundations will give us similar things. And again, using near-infrared spectroscopy, these were all the various different types of foundations that we tried. There was no pre-treatment involved. We tried different shades, different versions, different types, different formulations. And of course, every brand, not only will they have a version of a type of foundation, but they will also have the latest matte version or the latest one that has iridescent particles in it to make you sparkle even further. So there's further noise to consider as well. So at this point, we're thinking, right, these spectra all look very similar. They all look the same. So how can we tell the differences between them? So this is where we started using some more advanced techniques that doesn't necessarily rely on instrumentation. So what we've used here is a technique that's called principal component analysis. And this particular technique works on the concept that we'll be able to reduce any of the dimensionality of the spectral data that we have. So in essence, if we're trying to investigate what cosmetics contain, it's able to identify for us that if there are differentiation between different brands, and if we can actually cluster the brands together. So it's a good, real nice and simple way in which you generate your data, you put it through the instrument, and it can help you start reading any particular patterns that exist, but also it can reduce the complexity in the data that you have as well. So let's explain PCA a little bit more in a bit more detail. So if you imagine paints, there's loads of different paints that exist. Different brands have different ones. They all contain different amounts of red, yellow, blue, different versions of the primary colors. What the PCA does, it finds the pattern in the colors, and it helps us to reduce things such as looking at just focusing on the most important color mixtures rather than looking at the rest of the noise. So if there are similarities between them, and it will ignore the similarities, and it will only highlight the differences that come between them. So in this case here, we just focus on the data and make sure that it's easier to understand. Here's just a diagram that shows it a little bit easier to understand. So what you've got here is you've got your paint data. You've got a paint tin that will contain certain amounts of blue, red, and yellow. And in this example here, it interlaps between the amount of blue and red that exists in that one paint sample. And what we've termed these as is principal component 1 and principal component 2. So essentially, it means that the differences that exist between them, they're all clustered into one side. So essentially, if we were to use this technique and take an unknown sample then and put it through our instrument, then run this software again and generate it to work out what the unknown is, it should be able to populate where it fits on these clusters. And if those clusters identify that it is of the same variety, it should nicely populate together. So some of the research that we did when we looked at this is that we had some promising methods proven to begin with. So it's sensitive enough to be able to distinguish between different chemical composition on most shades of foundation that we had. And in this example, you can see that 93% overall, it showed us that you can distinguish an unknown and try to work out whether it originates from the same source. So this table over here, all this table is demonstrating is simply the different types of samples that we had. How specific were they to be able to fall into that particular category when we ran an unknown of that same type? How sensitive was it? How accurate was it? And also, was there an opportunity for false positives to be identified? False positives in forensics are really important because they're a way in which we ensure that we are going to actually be testing something positively and it's not coming out as a false positive instead, something that replicates what it should be. A good example is sometimes when you're doing testing for blood, there's a certain type of chemical that exists that is mimicked sometimes by a particular fruit or vegetable, and that can sometimes end up with a false positive, glowing and highlighting that is blood there. So that's just an example there showing how we use this for looking at foundations and how it was able to work quite well in distinguishing overall 93% of the time it was successful in identifying what brand and particular shade even the foundation belonged to. Okay, so what I'm going to move on to explain now is one of the other techniques, which is chromatography. And I'm going to do a very quick demo for this. So for this, it's to do with separating mixtures in components. Some of you may be familiar already with this technique, but when you have a particular substance, such as a dye or any type of other chemical material, there will be loads of other components that exist inside that one item. It could be one thing that sits in a biological substance, or it could be something that's often in complex mixtures. So I'm just going to come around here and just quickly demonstrate how we would expect to see this. So what I'm drawing essentially on here is something that is known as something that we normally use as a TLC plate, or sometimes known as a thin layer chromatography plate. What this will demonstrate is how you can separate mixtures using one flat stationary phase that doesn't move, and then we'll have a mobile phase in there, which will be something that moves. So I'm just going to put a dot on here, which essentially would be our ink, for example, and I will just add this into the TLC tank. Put a little bit of water, which acts as your mobile phase. And when you're doing these techniques on a larger scale in laboratories, the actual substance that you use, in this case I'm using water, but when you're working in laboratory, sometimes that water is pushed through at different rates, or it's pushed through using high pressure. And sometimes you don't even have water at all, or a solvent at all. What you would have is what's known as a gas, for example. And that essentially is what's enabling this mixture that exists in this black dot to move through. And so what we'll do is we'll revisit that again, because it will take a little bit of time to separate it out. So we'll switch back over to the slides, if that's okay, whilst that nicely develops, hopefully. So that concept of chromatography essentially is when you've got a mixture. So in this case, the mixture is simply the black pen that we've got here. And inside this black pen, it's made up of various components, whether that's going to be the dye, the different type of preservatives that might be present inside here, or the different types of inks that you have, because it's not necessarily just black ink that you have. So that should hopefully nicely separate out, showing a version of different colors, and that is the concept behind how chromatography essentially works. So let's move on to how chromatography is involved in actually looking at forensic analysis or forensic chemistry. So not all crimes involve bodies. So in this case, I'm going to talk about a case of food fraud. Technically, when you're looking at food and you're looking at fraudulent activities that exist with food, you might think, how is that forensics? It is forensics because you're actually identifying the cause of something that's happened. So in this case, we were trying to, well, we weren't, but they were trying to, back in sort of 2013, they were trying to identify the horse meat scandal and whether there was actually horse meat that was present in some of the meat that was being produced or sold. So in this case, 27.2 of food fraud is normally within meat and meat products. So that's quite a high percentage of fraud that might exist. Chromatography can be used very accurately to try to identify what the meat is made up of. So in this case, you could use chromatography to be able to highlight some of the proteins that exist inside there, coupled with other techniques. And you could also use it to be able to identify whether the meat contains only a version of meat or if there is anything else in there as well. So a lot of this was research that was done many years ago, but they've been updating it ever since. And you can see that with this research, they were able to identify that food itself contains various different things inside it. So you could essentially test what one food might be and then compare it against another food to see if it has originated from the same source. So again, forensics again. And you might be able to then go back to the laboratory where the food was perhaps first tested or first made, or in the manufacturing site, and you could pinpoint down where the source of contamination originated from. So, another very tangential move here now. I'm going from food to tyres. Tyres, how is food and tyres related? How bizarre. Well, actually, the way in which they're both related is that they both contain different chemical profiles. Not only are they chemical profiles in the constituents that they're made of, but equally, they're made up of very complex compositions. When you look at food, it contains preservatives, additives. It contains the various components that keep it to have shelf life, to keep it to be as it is. Complex mixtures for tyres is also very similar. So when we're looking at tyres, the reason why we're interested in this is because data that showed us in 2021 that nearly 2.5 times as many hit-and-run casualties are on London roads as they were in 2009. So hit-and-run cases are becoming much more high compared to previous years. However, this data is very complex, and this was from a report that was generated a while back. Some of that data can be very complex, and again, this is to do with that noise that we're referring to. What tends to happen, as you can see on this image here, is you can see tyre tracks or skid all over the road there. And what forensic scientists routinely would do is they'll look at the tyre tracks and compare them to the tyre treads, perhaps, to identify what tyre perhaps would have been used at this scene. And what would be useful would be to know actually chemically what does this tyre contain. So you can see where I'm going now, the composition of tyres and how they're so important. So when we're looking at complex tyres, you can see here that tyres are made up of natural substances, natural rubbers. They're also made up of synthetic rubbers as well. And those synthetic components, they are normally in different variations and different combinations. And depending on one brand to another, so you might have a Bridgestone, you might have a Pirelli, again, many different various brands are available, but they're the ones that we were just exploring. With those different brands that you have, there will be a different percentage of each of those because each tyre brands their version with their own patents and sort of the way in which they manufacture them. Nobody else can use that particular method. And also you get ones that are anti-skid, ones for snow, ones for this. The list goes on. They also contain things such as antioxidants, black carbon. So all these different various chemical compositions that exist within them can complicate the picture and provide more noise for us. As I said, particular brands, they have their own versions. So you might have a Bridgestone that has 27 different tyres that all do the same thing, but they decided to have slight different variations of them just because that's what the market wanted. Also, different brands, so Bridgestone will patent their own version, but then Pirelli will have their own version of something as well. So when we're looking at the road surface, that is also noise as well. When we're saying noise, if we were to go up to a floor or a road where there is some tyre treads that have been left behind or tyre skids, and we wanted to collect some of that tyre sample and then analyze it using some chromatography techniques or spectroscopy techniques, any technique, it will also contain some noise from the road as well. That noise being whatever is on the road, pollution, however it may be. So we have to bear these things in mind. So some of the research that we were doing at the university was looking at the constituents of tyre and looking at the debris that was left on a physical surface and have a look to see whether they're able to identify what particular tyre or brand that tyre may belong to. And this is alongside using physical examination. So alongside using the tyre tracks, the traditional methods that you use, we're trying to chemically identify things as well. So we had a PhD student that was set up and built their own rig. So they had their own sort of rig that was made up with a tyre spinning around on a surface and creating those particular marks for us in a controlled surface. So that controlled environment meant they were able to scrape away small amounts and then start running those through the instrument to then build a database of what those tyres looked like. But it's not that simple because unfortunately the instruments don't work with solid particles. So you would have to do something to those particles before you can inject them into the instrument. So in this case, you can see from this picture here, you've got your rubber that's on the left-hand side. So this was rubber that was taken directly from the tyre. And then you've got your skid mark samples on this side here, which were left at, say, for example, our controlled environment where we had the wheels spinning around, continuously creating those skid marks on the floor. So those are solids. We want to get them into a liquid. So what we normally do is we use a process known as rubber digestion. And this essentially means that we would expose it to a high concentration of a particular acid. We then expose it to a microwave to digest it, not your standard microwave at home, but it's a different type of laboratory microwave. You expose it to that environment, and it speeds up the process of breaking it down, the solid, into a liquid, and therefore that liquid will then be suitable for running on the instrument. So that's how we prepped the sample then. We then ran it through an instrument, and on that instrument, it was able to identify to us that this is what the Michelin tyre looked like, and this is what the Bridgestone tyre looked like. And those peaks that you're seeing there, those different types of peaks, just simply represent the chemical composition of the different types of tyres that were used. So each one had their own chemical profile. And those chemical profiles are very useful to us because they can help us identify whether a tyre belongs to a particular brand, a very subsection of a brand, and also we use pyrolysis GC. The difficult thing with using things such as rubber normally means that it needs a very high temperature to be able to burn and form into a liquid. So that's why pyrolysis GC is an instrument where we use chromatography, but it does it at a very high temperature so it can break down things very quickly. So I'm just keeping an eye. Can we just cue back onto the visualizer, if that's all right? Thank you. So if we just look back now at the visualizer, you can see this has now separated out, and no longer was it that black spot that we saw before. It's now gone into various different colors. So that shows you that one black dot that you thought was actually just one substance is made up of other different chemical constituents that you see there. So that nicely demonstrates that concept of chromatography, which essentially, if we just go back to the slides, thank you, which essentially is what we're doing in this particular thing as well. It just looks different on the chromatogram that we have here. On this information that we're seeing here, it's just simply highlighting to us at different points when it's running the sample, at different points there's something that's coming out that's different to what was before. So why not apply the same concept to what we did when we were looking at cosmetic analysis? So we've used principal component analysis again, and what we're doing this time is we're looking at the amount of metal that is present in the tyres. So what we did was we used a separate instrument, and this separate instrument enabled us to be able to identify specifically how much of these 10 metals exist. So how much aluminium existed, how much titanium existed, how much chromium, cobalt, nickel, and so forth. And what it did is it put it into different clusters. So all the Pirelli tyres were here, all the Michelin ones were here, Bridgestones were here. So again, similar sort of concept. In theory, the same thing should work. If we take an unknown, run it through the instrument, and then run it through this particular PCA software, it should be able to identify to us what brand it belongs to. These results effectively showed us that there are differences that exist between similar groups of tyres, and we can actually pinpoint down the brand, but also the sub-brand within that particular tyre as well. We also use infrared spectroscopy, so a technique that we came across before, to complement some of this work to see does it work alongside that, or does it only work with chromatography of the tyres. So we did it for this one as well, and again you can see it nicely separates out with different types of tyres that you see. And then we decided that we wanted to explore it further, and now we're exploring ways in which some of the advances might be on the road ahead. So some snapshots, just to kind of finish off of where I see the world moving towards, the passion for forensics and how it will evolve. Hopefully we'll start seeing now more advances in some of the portable instruments. Portable instruments have fantastic advantages that they can be done on the field. In other words, they can be done at the crime scene without all that analysis having to be done in the laboratories. These instruments can be developed to work in the crime scene or even work at another remote location where it quickly gives you preliminary results. Having said that, it doesn't mean that the jobs of those that work in the laboratory are not going to be there. It just means that preliminary tests will save a lot of time and be much more effective in sending samples to laboratory afterwards. And also, the word that is used quite a lot nowadays, digital technology, AI, and machine learning, will it speed up the process? Will it enable us to be able to model certain behaviors? Will it be able to see whether we can identify particular brands of cosmetics, tyres, if we were to just simply have a database and then model what might come out of it? So I just thought I'll provide this very nice image here of what might be the future of some of these portable instruments as you go on to scenes where some of that versatility would be able. The future of forensics is going to be really uncovered, I think, as we start seeing a lot of the digital technology coming out into the techniques that we already use. And hopefully that will enable us to be able to get faster results for when it comes to research, but also techniques can then be embedded into the actual forensic process itself. So hopefully that was a very snapshot introduction or a snapshot overview of some of the research that we've been doing, looking at how we can advance the field of forensics, but keeping in mind that obviously all forensics, any research that you do starts off small and has to be built upon, and this is where we are at the moment. Just like to say thank you to Kingston University for providing the support and the foundation to be able to undertake some of this research. Some of my collaborators, Professor Brian Rooney, we have our own CAST forensic laboratory in the university, so it's an accredited laboratory that undertakes toxicology work, so it takes toxicology work for blood analysis and for drug analysis, and it works on caseworks. Some of the student researchers that have been working in this field, helping build up some of this research that's still undergoing publications. Also, I'd like to thank my husband and my son who constantly keep me inspired and keep me curious. Their curious minds always make me think, how can I make it more understanding and more accessible for everyone to enjoy chemistry as much as I do? And finally, I'd like to thank all my family and friends as well, and you as an audience, you've been absolutely fantastic. Thank you very much. Thank you.